before you started. All right. So the first thing we'll do today is to go over the homework assignment, and from the lack of people in the classroom, I'm assuming some people was frantically working on the homework assignment and on their way to the classroom as we speak. Hopefully not on their way home as we speak. Okay. All right, but this wasn't really supposed to be a really difficult homework assignment. That was not the intent. Is to stump people, even though we do have the entire break in between. Maybe that's why it's hard. I'll blame it on the break.
Well, only if you didn't do anything.
Because sometimes it's hard to pick these concepts up again, after a break, because without exposure for an entire week, that's a pretty long chunk of time. Okay, so what I'll do is I'm going to do the homework assignment myself, and I'm going to show you how I would have done the homework assignment, and I'll do it step by step. Okay. The first thing I would do is to write it in C or C++, or in some high-level programming language that you are familiar with. But since cisp310 is a prerequisite to this class, I'm assuming that everybody knows C already. So that's exactly what I'm going to do, is to write a C program to do exactly what this program is supposed to do. And in fact, I'm going to use the same thing, which is the same folder, string count, and do all the same thing here. So we'll create a folder called string count. Oh, it's already there.
Yeah.
And inside we already have a C program. Okay, great. So I'm assuming that you guys took a look at the C program, because that's actually something that I talked about in one of the classes before the break. And to go from here to the assembly code is really a matter of flattening the program first, and then convert everything to simple comparisons. Okay, so let's go ahead and do the flattening first. But before we do the flattening, do you guys remember how to test the program? Okay, so when I test the program, okay, forget about the recursive version, because we are not quite at the point where we can talk about recursion yet, so we're not going to use the recursive version. But this is just one test, counting the number of lowercase a characters in the string. This is a rather long string. Okay, that's one of the test cases. You definitely can change this, to do whatever kind of test you want to do. Before we go any further, let's see. I think this will work. All right, so I'm going to change the code in C first. One thing you might want to do if you're changing the C code is to back up the version before you make all the changes. So this way you keep a extra version, so that if you need to go back and say, okay, I messed up the logic, it doesn't work anymore, you can compare your flattened version of the program to the previous one, so you can tell, okay, what did I change in this program to make it not work? Okay. But I'm not going to do that because I kind of feel like taking risks today. All right. When you do the flattening, don't do all the flattening at the same time and then test the program. Because if you did that, and then if the program doesn't work anymore, then you don't know which part of the flattening is making the program not work anymore. Okay? So don't do that, and instead just do one thing at a time. Flatten one thing, and then test the program again. Flatten another part, test the program. So this way, if after one particular flattening the program stops working, you know exactly what change is responsible for breaking the program. Is that making any sense? Okay, I know it sounds like, oh, but that's going to make it take longer. But in the end, I think in most cases, it will take up less time, because you can easily diagnose the problem and pinpoint where the problem is. You can start with a while loop. You can start with the conditional statement. It really doesn't matter which one you start with, because we can do it one at a time. I'm going to start with the conditional statement. So what I do is I will comment out everything that should not be there anymore. Okay? As the term flattening implies, we won't have structures anymore. Curly braces are the indication of structure, okay, because they're basically a container. So I'm going to take out everything that is structured and replace it with the equivalent logic, but without using structure at all. So in this case, we are basically looking for the inverted or the negated condition. So we are saying if whatever EAX points to does not equal to BL, then we want to skip the then block and go to the end if label. Okay. And the end if label is going to be at the end of the construct, like here. So that would be the first step, is to flatten the conditional statement so that we don't have actual conditional statement anymore. But tech, you still have the conditional statement if EAX does not equal to BL, go to blah, blah, blah. But that can easily be done using a compare instruction followed by a conditional branch instruction. And that's the whole objective of flattening, is we want to reduce everything to a point where it is easy to implement using assembly language. Okay? So now the next step is to deal with the while loop. So once again, I take out everything that is structured, including the word while and all the curly braces, and replace it with labels, conditional branches, and stuff like that. So it's not structured anymore. So this is the label while begin, because I need to go back to this point at some point, and that point is going to be at the end of this loop here. It has an unconditional go to while begin. Oops, there we go. And then at the very beginning part of the loop, I have to check the condition. So I have to say while EAX, oops, I have to invert the comparison. So it is while not EAX or whatever EX points to, go to while end. And then we have while end over here. All right, so I'm done with all the flattening now. In other words, the program as it is right now is clumsy. It does not make use of structured programming concepts, but it should functionally speaking, it should still do exactly the same thing as before. Is that okay so far? So let me ask you the three questions. Are you guys okay with the how? The actual steps of flattening the program. The what, okay? What did we just do? We got rid of the structured programming constructs. And then the why is because we want to implement all the logic of this program using assembly language. And at this point, okay, there's only one thing that is not expressed by a comparison and then a go to, which is this guy here. How can I rewrite this condition so that it does involve a comparison? There's an implicit comparison here. It is sorry?
To 0.
To 0, exactly. So there we go. So if whatever EAX points to is the null character, it's time to exit the loop. Go to the label called while end. So I'm pretty satisfied with the flattening, but if I'm actually doing the homework assignment, I'm not just going to take this code and go, okay, now we are ready to convert it into assembly code. I'm going to test this program. In other words, I'm going to recompile this program. It is still compilable. This is all C and C++ constructs. So I'm going to compile the program with debug option. So string count.c. Wow, I did not make a single syntax error. It's kind of rare because I typically would put in something, like a colon instead of a semicolon, something like that. Okay, that's gdb string count. List the program, put a breakpoint on line 40, and let's do the counting by hand first. Okay, so we have 1, 2, I think there are 2 lowercase a's, so x should end up with a value of 2 in this case. So run the program and print x. It is 2, so I am fairly sure the program does work, but if I'm not sure, I will test it with more test cases just to be sure that the logic is preserved. Are we doing okay so far with this particular assignment up to this point? Okay. All right, so once I'm convinced that the flattened program is working the same way as the original program, then I can start to convert it into assembly code. Okay. The way I do this is to copy the C code over to the assembly source code. So I have to do some editing first because everything has to start with the comment line, the comment symbol, and to do that in VI is not too hard. Like that. So everything now starts with a pound sign. They're all comments at this point. So I can now add the other stuff that I need for an assembly code program. So underscore start is a global label, and underscore start. So I basically have to mirror, this part here, or I can just copy and paste. Either way is fine. In fact, I just feel like copying and pasting. So copy, get out of this one, and we say cat double greater than string count.s. So this time I'm using not a single greater than, but two greater than, which means append to. If I have a single greater than, it simply means redirect the output to overwrite the original file. When I have double greater than, it means append to the current file. So I'm not destroying the content of string count.s, I'm just appending new stuff to it. Okay, press the enter key, do the paste inside. You can do this in PuTTY, but you cannot do it on the console of the virtual machine. Control D at the very end to stop the process. And now we can go back to the file. Okay, now it has this part here, which is no longer needed, and it has the other part here. Okay, so I'm supposed to put my code over here, so I need to copy everything earlier to this point. So I need to look at the line numbers. So I'm moving MOVE. I'm moving line 1 to 43 to here. Okay, let me see if that works. Nope, valid address. Fine. 1 to this point. Delete and paste. There we go. All right, so now we have the entire chunk of stuff over here, because this way I can do the conversion line by line, and I know what I'm converting. All right, the initialization is done for the most part. EAX is initialized, BL is initialized, but ECX is not. So I need to make sure that I initialize ECX over here. And it's a pretty easy initialization. We just want to put a 0 into registered ECX. Okay. The next one is the label definition. Label definition look exactly the same way, regardless of whether it's in C or in assembly language. And then this line is going to be a combination of two instructions. The first part is going to be a compare instruction. A compare instruction is just really a subtraction instruction without storing the result. But we are relying on the side effect of a compare instruction, which is changing the flags. The 4 flags, the Z flag, the C flag, the O flag, and the sign flag. Okay? So the first thing we want to do is to compare, but this time you have to choose very wisely which compare you use, and also the operands. Okay? So the first question is, I know it's a compare, but if I just say CMP, that may not work, okay? Because most of the time CMP works by itself without the B, the W, or the L, because from the context of the operands, the assembler can pick the correct width for you, okay? Whether it's 8, 16, or 32-bit, but not in this case. Because in this case, what are we comparing? We are comparing the constant 0 with whatever register EAX is pointing to. The constant 0 does not indicate the correct width, because 8-bit can represent 0, 16 bits can represent 0, 32-bit can also represent 0. It does not suggest a width. What about the second one? It looks like EAX is suggesting a width already. Well, yes, EAX is 32-bit wide, but what it points to can be 8, 16, or 32-bit wide. So in this case, neither operand is suggesting what is the correct width, and without spelling out the correct width, the assembler is going to assume it is 32-bit, which is a long. And that won't work. That won't work because when you terminate a string, you're only guaranteed with a single null character. There's no guarantee of what is after the null character. So that's why this is not going to work. You have to make sure that this is a compare byte instruction to force it to only compare to one single byte and not 16 or 32-bit. Okay, and I think this is a tricky one because in many cases we don't really care about the width of the operation. In this case, it is important, and there's nothing else in the instruction to suggest what is the correct width. Okay, but this comparison by itself is only doing the comparison. It does not even confirm one way or another whether EAX is pointing to a null character or not, because it is only setting the flags that we can rely on. So you have to follow that up with a JZ instruction, because when you do the subtraction and the result is 0, that means EAX is in fact pointing to a null character. So in that case, we can go to while end. Okay. Are there any questions about lines 24 and line 25? Why this is going to implement the pseudo C, well, the actual C code of line 23? Questions? No questions? Okay. So if there's no questions, we'll move on. The next instruction, or the next line of C code that we have to do the conversion, is line 28. Line 28, once again, is a comparison followed by a goto, so we can do a comparison operation. Okay, CMP. We are comparing whatever EAX points to BL. And this time, well, I guess it doesn't really matter the order, because we just need to know whether they are the same or not. But the typical way that I do things is I will do something like this. I would reverse the direction of, or reverse the order of the comparison, because then I can translate more directly, especially when this involves less than, greater than, that sort of thing, where it's not commutative. Inequality is commutative, so it's not going to be a big deal. Okay. So this time I'm comparing BL to whatever EAX points to. Now on line 29, if I do not specify a W or B or L, it's going to be okay, because the assembler will look at this instruction and say, okay, can I infer what is the width of the operation? There's one operand that suggests the width, which is BL. Because BL is an 8-bit register, there's no way around that one. Okay? In fact, if you force the compare instruction not to use 8-bit, if you try to do something like this, the assembler would actually complain and say, hey, something is not right here, because the operand is suggesting this is an 8-bit operation, and yet you are trying to use a long operation. It's conflicting. The assembler would actually complain about this one. But it is always good to specify the byte operation manually, just so that we don't make a mistake. Yep.
It'll give you a warning message, yeah?
I think it is just a warning message, but I'm not 100% sure. Let's make it complain, and we'll see what kind of error message it gives you. Okay. All right. So this is just to compare. We have to do a JNZ in this case, because it is if not equal to, go to endif. So that's why it's a JNZ. JNZ to the label that marks the end of the conditional statement. So we are now done with this line. Plus plus ECX is just adding 1 to the register ECX. Okay, so that's a pretty easy one. And if the label definition, just uncomment, because it looks exactly the same whether it's in C or in assembly. Adding 1 to EAX is just add long 1 to EAX. Go to while begin, which is an unconditional branch, is JMP and then the same label name. Label definition while end, just uncomment, because it is the same syntax. There's nothing to return, okay? I'm just going to check the value of ECX. The rest of this program really doesn't have to be here, so I'm just going to delete all that stuff here. And now I have the assembly code interleaved with the C code. If it doesn't work, at least I have a reference and say, okay, this is what it's supposed to do. If it's not doing that, something is wrong. Okay? So now I'm ready to test the assembly code. Let's go ahead and see if we have some test cases. I think we do, because I used this to illustrate how to test the program. Cat test.0 is not going to be enough, because it won't show the null terminator. I want to make sure that there is a null terminator in this particular string. So the other way to do this is do a hex dump -c test.0, and this time you can see the null terminator is here. Are we doing okay so far with double checking the test case just to make sure that the test file has the proper content in it? Is that okay? All right. Okay. So the next thing to do is just to assemble, link, and then go into GDB just to see whether the program works or not. So we'll first assemble gstabs -o string count.o string count.s. Okay, so it is an error. Okay, so I stand corrected. It is not a warning. It is an error. It does not give you an object file to link because of that mistake. So we'll go ahead and change that. In fact, we found 2 errors because I forgot a colon after underscore start. Okay, I forgot my own instruction in class. So we'll fix the label definition first, and then we'll locate the instruction, change it back to compare byte. Reassemble, no problem. Link, and check out program. Okay. So when we check out program, I think I created a source, a debug script just to do that. So let's check. So let's check out debug1 because I think that's the file that will do it. So debug1.gdb is just a little script. All it does is to load the content of test.0 as a text file into the address of string. Yep.
Sorry to interrupt, but I think you need to write like breakpoint at 3, then R, then after those 2 things, you'll put continue, and then IRC, and then it'll automate everything. Because remember we had that issue.
Right.
Yeah, I couldn't run mine unless I hit run first, and then.
Yes, you have to run it first.
So you can actually write all that in there, though.
Well, if you put a breakpoint, if you set a breakpoint in the script, then it will put duplicate breakpoints every time you run the script.
No, but then you'll just put continue after the set var, so then it loads everything before.
I think you need 2 scripts if you want to automate everything. You need 1 script just to put a breakpoint in. So you want to put a breakpoint.
Well, it worked for me, so.
Okay. So we want to put a breakpoint in well, yours will end up basically putting multiple breakpoints at underscore start, which is not a problem, but it does end up with multiple breakpoints.
No, I had one breakpoint in the beginning, 1 breakpoint at the end.
Right. But did you set the breakpoint inside the script?
Yes, inside the script.
Yeah. Then every time you run the script, it will create a new breakpoint, unless in your own script you also undo the breakpoints at the end. All right, so the way I do this, I have to do certain parts manually, like setting up the 2 breakpoints and then do the R. That part has to be done manually. And then the rest, I can now run it using source. Now we are at the end of the program. Nope, it didn't continue. Okay, so now we have to press continue. Now we're at the end, IRECX. Did not find. Did I load anything into kchar? Okay, maybe I did not load everything. We're looking for lowercase a, and then test.0 has 1 a here.
2. Rather.
Oh, rather has another one. So there are 2 a's. So my code is not working. It's not counting correctly. Well, that's good because now I can debug the program. Okay, so the program isn't working, which means when it's supposed to be incrementing ECX, it's not incrementing ECX. So the question now is, it is supposed to get to line 33. It did not get to line 33. So that means it could be several things. Yep. Let's see.
Plus.
Yep, I did. Yep, so there's this one here, and then it goes back to the beginning. Okay, so let me just kind of go through the debugging process because I know most of you know how to debug the program, but I just want to kind of talk about this. Okay, so my code is supposed to get to line 33 to increment the count because in fact it should go there twice before it gets out of the loop, but it's not. Okay, but there can be multiple reasons why it's not getting there. The first one is the conditional statement is not set up correctly. In other words, line 29, line 30, they're not doing what they're supposed to. So let me just double check. I'm comparing EAX or whatever EAX points to with whatever DL has. If they are not the same, I go to NIF. So it will skip over when they're different. When they are the same, it should not skip over and actually add one to ECX. So that one is not a problem, but there's a second chance of it doesn't go through the loop at all. The loop exits right away. So there's also that chance. So let's double check and make sure the loop does not exit right away. That will be on line 21. Line 21 is while begin, and then we compare whatever EAX points to 0. If it is 0, we go to end, while end, which goes all the way to the end. Otherwise, it should go through the loop. So right now, none of this is explaining the behavior of the program. So what do I do next? I can use the same test case to test the program again.
You make it smaller so it's easier to go through.
Exactly. So we can make another test program. CP test.0 to test.1, vim test.1, and we'll put an A at the very beginning. So the first character should match already and go through the increment. So this way it's just quicker to test this one. And I'm going to copy debug 1 to debug 2 just to deal with the second test case. Like so. Run. Okay, I'm just looking at this code here. It will run, it will hit the first breakpoint. I do the continue, and they should get to the second breakpoint. Okay, just making sure. So GDB, the same program. I haven't changed the program yet. Put a breakpoint at underscore start so I can set up everything. Put a breakpoint at check here where I should really be checking ECX. And run the program. Ooh, I know why.
Maybe
It has to do with the script itself. Yeah, it has to do with the script itself.
The run.
Because of the run.
Thought so.
Yep, that's it.
Not exactly, but.
Okay, so that's why. Okay, so the script that I have here is only good for loading the test case, but it's not good for running it. So now I can continue execution because the script set run, which will reset the memory all the way back to all zeros. So that's why it's not working. So now it's just continue. I get to the end of the program, print ECX or IRECX, either way works. It is 3, it is correct because I have one additional one at the very beginning in this case. So it did work the first time, it's just that my test procedure is wrong. All right, so are there any questions about this whole process of writing the code, testing it, debugging it? It's all good? Yep.
Zach, could you do you mind if I have warning messages in there? I mean, it works. But
You mean when it assembles?
yeah.
What kind of warning did you get?
Well, it's saying that instead of using ECX, you should be really using
CL?
CL, and when I did that, it wouldn't increment after a certain amount of numbers. So
But why didn't you fix it?
No, well, it worked like that. In the directions, it didn't say that it's supposed to.
But it's not a good idea to ignore warnings.
No, it's true. It's true.
Unless they're bothersome.
It works.
I did not say in the homework assignment that you have to assemble the program without warning. So from that perspective, I don't have any excuses to take any points off.
As long as it works.
However, there's a big however in boldface, okay? It is not a good idea to leave warnings unresolved. Okay, so it doesn't matter whether it's a warning from the assembler, from the linker, or from a C compiler. If there's a warning, it's trying to tell you something that's potentially problematic.
It's trying to
So-
warn you. It's trying to warn you.
It's trying to warn you. It's trying to save you, actually. Okay, So from that perspective, I would highly recommend that you get rid of all the warnings in your programs in the future. So would that work? So I'm not going to take any points off, but I will still so since you ignore the warning and the nagging from the assembler, it is now my job to give you the warning and the nagging. So we're taking a step up, I'm the soup. Yep.
And is it okay if I just, instead of using loops, I just use breakpoints and just bounced around?
I'm not really sure what you mean by that.
Like I had, like L1, L2, L3, like semicolon. So not
No
the
colon.
breakpoints in GDB, but the
Labels.
labels. Yeah, sorry, I was just.
You can use
Yeah,
labels.
I just had a bunch of labels and I was bouncing around.
We aren't allowed to use labels.
Oh, okay, so your
Instead
labels
of-
are not named the way.
Yeah.
Oh, okay,
yeah,
that's fine.
Instead of
Yeah.
using those loops,
Yeah, well,
It makes it less nice for
it's
dogs
just
back.
easier for me
For
to
you
keep
to
track
understand,
of
yeah.
the labels if I name those labels like if and, while and, and stuff like that. It just makes it easier for me. But if that doesn't bother you,
It's my first time, so.
yep,
Yeah.
that's all right. Okay, so any other questions about this particular homework assignment? No questions? So you guys are ready for the next one?
Yeah.
Okay, so let's talk about the next homework assignment. What? The next homework assignment. We are now into subroutines, so the next homework assignment is related to subroutines. And we'll talk about the call return instruction, after we talk about the homework instruction. The homework description itself. So recursion one is the first homework assignment when we deal with subroutines. So what I want you to do is to implement XYZ. XYZ is a subroutine, and it doesn't have any return value because we haven't talked about how to return the value of the subroutine. It doesn't have any parameters because we haven't talked about how to pass parameters to subroutines. It does not even have local variables because we haven't talked about local variables in the subroutine. So X is a global variable, and so is Y. They are global variables. So I just want you to do this in assembly. I want you to do this function in assembly. And if you look at the instruction, we don't even need to deal with X and Y. Because according to this instruction here, I want you to use register EAX as variable Y, which is a global variable, and I want you to use register EDX as variable Y, which is also a global variable. So you don't have to deal with anything that is a local variable, parameters, return values, and all kinds of stuff like that. Just use these registers as your tools. Okay. You can also use other registers if you feel a need to use EBX for something. Go ahead. If you need to use ECX for something else, go ahead. But ultimately, I will focus on these two registers after the end of your subroutine to see if it comes up with the right result. Is that okay? All right? Okay. So your job is to basically just copy and paste this little chunk of code here. It has two labels. Okay, this label is not really needed because it's the same thing as underscore start, but this is the label where I would put a breakpoint and I will initialize the registers with certain values to test your program. The second label, which is check values, is right here. This is where I would stop the program again just to see whether Y has the correct value or not, based on the initial value of X. Okay, so this is how I can test your program using a script, is by setting breakpoints at these particular labels, which also means when you turn in your homework assignment, you have to make sure that your labels are named exactly the way they are listed here and located exactly at those places. Okay, the call is in between. Okay, this is the first call to your subroutine, to your code. And your code can go here, okay, after the program itself. You can also go before, just not somewhere between underscore start and the rest of the program. Are there any questions about how to set up the code that you're going to write? No questions? Is that okay? All right. This is the actual code in C, in regular C code. I actually tested it. It does work. It does compile. Okay. So the first thing you want to do is what?
Check it out.
Flatten it? No. You want to see what it does first. Okay. So you want to compile your program, but this program won't compile as a self-contained program because we don't have main. So you have to write your own main, initialize x to 0, see what it does, initialize x to 1, see what it does, initialize x to 2, and see what it does. Okay? I think by the time you get to 3 or 4, you will know what it does. Okay? In fact, if you're really good with your math, you would know what it does right away already. It's like, oh, okay, I can see that. Especially if you come from CISP 440. This is something that we saw a little bit earlier, just in a slightly different format. But at any rate, you want to know what it does. Now, even if you look at the result and go like, I do not see any pattern, it's okay. You don't have to see any pattern. All you have to do is to say, when x starts with a particular value, y ends up with a particular value. Write it down on a piece of paper, a spreadsheet, or do something to remember that, because your assembly language code is supposed to do exactly the same thing. So you just need to know what your assembly code is supposed to do when you run that code. We'll go through this step by step. Do we know how to compare and confirm something is less than or equal to? Okay, and x and y, by the way, are both unsigned. Okay, so when you do compare, you'll make sure that you pay attention to the flags that only relate to unsigned numbers. Do we know how to subtract 1 from a register? Yep. Do we know how to call a subroutine? Well, we're going to talk about it today, but it really is just call XYZ. Okay, I can tell you that right away. Do we know how to do this? No, we don't. Yes, we do. Okay, yes, we do. But we haven't really talked about the multiplication in this class. Yes, we have not. No, we have not talked about multiplication. But how do you do multiplication by 2 when you only know how to add? Just add it twice. Okay, cool. Adding 1, not a problem. And adding everything else to register EDX is another instruction. And this is where you might need to use register EDX or ECX as a temporary register, because you don't want to mess around with EAX or EDX. So you have to use the other 2 registers, one of the 2 other registers to get this done. No, I take it back. You don't even need a second or a third register. You just need the 2 registers to play with this.
Push it to the stack.
No, you don't even need to do that, because this whole thing is just y plus equal to x plus 1. So instead of looking at it as one line and try to do it on one line, do it with, let me see, 1, 2, 3. 3 lines, 3 instructions. Is that okay? Okay, so I'll just say it now. This one line can be done with 3 assembly instructions without using any other registers. So you only need to make use of EAX and EDX. You won't even need to use any other registers. If you do end up using some other registers, it's okay. I'm not going to take any points off, but I'm just telling you that there is a way to do this without using any other registers. Okay, this one is just adding 1 to x. Okay, not a problem, right? This one is just initializing EDX to 0, which is not a problem. So this program is in some ways easier than the previous program, because the previous program has 2 control structures. It has a while loop on the outside, a conditional statement in the inside. This one is just one conditional statement with a bunch of adding and subtracting and whatnot. Okay? But what makes this program harder is if the logic is wrong, it will end up with an endless recursion. you will run out of stack space, and the program will crash with a segmentation fault. Okay? So, but I already told you that, okay? So that means if you see a segmentation fault and your stack pointer, when you look at ESP and it's a very low value, you have just, missed the point where it stopped the recursion, which is indicative of a problem with the conditional statement itself. Okay? But that's the only thing. Oh, by the way, there's one more thing. What do we do at the end of a subroutine? Because in C and C++, unless you have a value to return, there's no need to use return as a statement. You can use it, but it's not going to do anything extra that it is not normally doing. So those are the two instructions that we'll talk about in the next, 10 minutes or so that you have all the tools that you need to get this homework assignment done. So are there any questions about the setup of the homework assignment? No questions? Okay. Yep.
Is there a reason why you pre-decrement instead of post-decrementing? Every other computer science teacher I've seen will put the minus minus or the plus plus after the variable.
Because, well, okay, they are really the same because nobody really care about the value of the expression itself. We're only using the side effect of adding 1 to x or subtracting 1 from x. So it really doesn't matter whether it's a pre-increment or post-increment.
In this case.
Sorry?
In this case.
In this case, yes. So in this case, whether I use minus minus x or x minus minus, it doesn't make any difference because the value of that expression is not used by anyone, right?
So it's just a preference.
It's just a preference, and I always assume the compiler is dumb.
Okay.
Okay? So if the compiler is dumb, then x++ can end up with more code because the value of x++ is the value of x prior to the increment. So the compiler may end up emitting some extra code just to get that, even though nobody cares. But when we say minus minus x, it's a pre-decrement, which means we are always just decreasing the value of x. So there's no extra code to reverse it back to the original value because somebody might care. So it has to do with my own background of writing compilers. Because okay, so let's do call and return. Okay, those two instructions. And the first thing we'll do is to go back to the browser here and talk about, so where do we read about calling and returning? How about this slide here? Does it look about right?
Give or take.
Isn't it? Okay.
Assuming it works.
It does. Okay, so calling and returning are done by two instructions, but we don't have to use those instructions. Okay. All right. So this is. This is how we call a subroutine. It's done by the instruction call. This is how we implement the subroutine sub1. It starts with a label of sub1, a label definition of sub1. Whatever code needs to go into the subroutine definition is going to be immediately after the sub1 colon, which is the definition of the label sub1. And then at the very end, we end with the instruction RET, which is return. That's how you write a subroutine. That's how you call a subroutine, just using call CALL, and then the name of the subroutine. And this is how you write a subroutine, which is starting with the label definition of sub1, put a chunk of code after that, at the very end, put an RET instruction. Okay? Are there any questions about the basic idea of how to call and how to define a subroutine in assembly language? No questions? Okay. So I'm not too concerned about the syntax of how to do something like this. I'm more concerned about what is really happening when we call a subroutine, what is really happening when we return from a subroutine, from the perspective of the stack and the stack pointer, what is really happening. So to illustrate that, I'm going to go back to my, well, not an emulator because I'm actually running it natively, but I'm going to show you a program just so that we can see, okay, how does that work? So we'll go to here and write a simple program to illustrate this point. In fact, I'll write a very bad program to illustrate this point. So I'm going to call this stack killer, because it is going to be a stack killer. Dot global underscore start and underscore start colon. And the simplest and shortest program to kill the entire stack is this. But that won't show you, well, let's do this first, okay? Let's do this first, and then I will show you how return works, okay? This one only shows you how call works, but not quite how return works. Is that okay so far? Well, we have seen a program similar to this one before using JMP, the jump instruction, right? Did the jump instruction, did that program crash? Or did it just get into an infinite loop and never got back? Sorry? Infinite loop, but the program did not crash. This one will crash. It will give you a segmentation fault, okay? So we'll go ahead and take a look at this program first. The first time we'll do it step by step. Look at the stack pointer, look at the stack, and then the second time or after that we'll do a continue and just let it crash. But after it crashes, we'll look at the stack pointer, because I will bet you out of this class, 1 or 2 people will end up with the same problem with your homework assignment. So I want you guys to know what can possibly happen when you have something like this happening. Okay, so as assemble gstabs-o stack killer.o stack killer.s. I'm just getting lazy, don't have to type the whole thing. sk.o gdb sk. There we go. So this is a rather easy program to track. Okay, so we'll put a breakpoint at underscore start, and then we run the program. Okay, this is before we make the first call. And I want to take a few notes here. I want to know what is the stack pointer. Okay, the stack pointer is at FFFE300. Okay, and we single step. Well, not very surprisingly, we end up at exactly the same location, because a call is going to start execution at the label that you're calling, but it is the same place. But what I'm really interested in is, what is the stack pointer? The stack pointer changed by 8 bytes, because we are actually running in 64-bit and not in 32-bit mode, so that's why it changed by 8 bytes. The question is, what do we have on the stack right now? Because I know the stack pointer is decreased by 8 bytes, which means I stored something that is 8 byte wide on the stack. So the question is, what did I just store on the stack?
Just some garbage.
Some garbage. Okay, so that's one idea. What do you think is on the stack right now?
An instruction?
The instruction. Okay, that's another guess. Okay, what else? Memory address, okay, but specifically what kind of a memory address are we talking about? Say again. So you wanted to underscore start, or the return address, okay, when subroutine is done, where am I supposed to go back to? Okay, all right, so let's see how we can find out where we are currently at this point, okay, which is the instruction pointer, also known as the PC. So EIP is the instruction pointer. Oh, this is not the, it's the 64-bit mode thing versus the 32-bit. So the name of the register is no longer the same. It's now called RIP because it's a 64-bit mode. That's why it starts with an R. So this is our current execution point. Okay, underscore start is 400078. Okay, so kind of keep a mental note of that. Okay, I want to know what is on the stack right now as an 8-byte thing. So we'll do a examine. I don't know how to examine something that's 64-bit wide. So let's see if help can help me with that. So we have, giant, there we go, G. So W is only good to 32-bit, so we need G to examine something that's 64-bit wide. So x/1G at wherever the stack pointer is pointing to. not access memory. Oh, I think it's RSP. There we go. Because it's the 64-bit register, stack pointer. But in your case, it's going to be ESP because you're using a virtual machine that is 32-bit in 32-bit mode. Okay. And I forgot to specify in hexadecimal, so that's why the number doesn't look right. In hexadecimal. Have we seen that number before? What is the difference? Well, they're off by how many bytes? What is D minus 8 in hexadecimal? D is 13, 8 is 8, so the difference is 5. And guess what is taking up 5 bytes? No, the call instruction itself is taking up 5 bytes. Okay? So if each call is going to consume 8 bytes on the stack, but there's no way out of the whole thing, it's going to consume more and more memory in the stack until we run out of stack space. Is that making any sense? So let's go ahead and continue the execution of the program, but we have to delete the breakpoint first, otherwise it will stop every single time we get to that instruction. And it does end up with a segmentation fault because we have run out of stack space. How do we know that we have run out of stack space? IRRSP, we look at the stack pointer, see how much it has changed. The stack pointer used to be, okay, I'm just looking through RSP here. So the stack pointer used to be here, which is 7F, FF, FF, E2, F8. And now it is this number. Just look at the least significant 6 digits, 7FF000, as opposed to FFE to F8. So the stack, we have just consumed this many bytes, 1, 2, 3, 4, 5, 6. We have just consumed this many bytes on the stack. This is a hexadecimal number. What is this number approximately in decimal?
A lot more.
A lot more. Okay. But we know how to do this conversion, don't we? Because we know how to count zeros. We got 1, 2, 3, 4, 5 zeros. Each zero accounts for 4 bits. So all the zeros here account for 4 times 5, which is 20 bits. Okay? 8 itself in binary is 1, 0, 0, 0. Okay? Because it's 2 to the power of 3. So 8 by itself is contributing 3 zeros, and then we have a single 1, and then we have 23 zeros. In other words, we're dealing with 2 to the power of 23. That's the number of bytes we have consumed on the stack. Well, okay, this is a power of 2, but what is this as a decimal number? Well, if you want to convert a power of 2 into an approximate decimal number, you use this rule. 2 to the power of 10 is approximately 10 to the power of 3. Because 2 to the power of 10 is 1024, and then 10 to the power of 3 is just 1000. We just say they're about the same. So we are basically looking at the number of 2 to the power of 10 in this number, and we have 2 of those. So that will make 1,000,000 bytes, and then we have the 3 left here. So we are talking about 8 megabytes in this case. So the stack has space for 8 megabytes. Once you consume all 8 megabytes on the stack, then you're out of space. Yep.
Is that a default?
I believe so. I think you might be able to change that just by writing certain things to the kernel file system. But it's 8 megabytes, which is actually usually plenty. Okay, you don't really need that much space on the stack unless you have a program that does not behave correctly. Okay, all right. So that's one thing that we can show is a program that just chews up everything on the stack. but it doesn't really illustrate how call and return works. So the next program is going to illustrate that. So this one is called return.s, which is going to illustrate how call and return works. So global _ start. And this time I will have the main program being here. It just calls a subroutine G, and that's it. Okay. Move $1 to EAX. All right. And then we'll have subroutine G here. G doesn't really do a whole lot. All it does is to call subroutine F, and then it does the return. Subroutine F doesn't do anything. It just returns right away. We'll just put a no up here just so that we can have something, quote unquote, something in the subroutine. So we have two subroutines. One is G, one is F. Neither does anything. One is just calling the other one, and then the second one doesn't do a single thing. Are we okay with this code, or do we have any questions about this code here? Yep, go ahead.
More to add something, if we're going to run this through GDB, shouldn't we put a something at the end for a label-wise? That way we can set a breakpoint and check out what.
We'll put a breakpoint at _start at the very beginning. Okay. Any other questions? Yep.
What is the int?
We'll deal with that later. It's an interrupt. It's a software interrupt. It is a request to the operating system to do something. Okay. All right. So, are there any other questions about this code here? Okay. If there are no questions, I am going to do something here. Okay. I am going to add some kind of random and seemingly useless label. I'll call this one after call G. Okay. And I'll put one here, and this is after call F. Okay, so these labels do not seem to make a whole lot of sense because there's no jump into these labels. There are no calls into these labels. They're just kind of floating around. Doesn't seem to be useful for anything. So we'll go ahead and assemble link. And then we'll go ahead and run this program and find out what it does. Put a breakpoint at _start at the very first instruction, and we'll run the program. Okay? We haven't really executed this call yet at this point, so the first thing we want to do is to check the registers first. Now remember, because I'm using a 64-bit architecture, I'm using RSP, but when you're using the emulator, you're using ESP for 32-bit, the 32-bit stack pointer. So RSP has this particular value at this point. We only need to pay attention to the last 2 digits or so. So this one ends with F0. Then we single step. Okay. So here's a single step. All right. At this point, we are at the beginning of the subroutine G, which is the label G. But there are several things I want to check. First of all, I want to know what is the stack pointer pointing at. RSP is 8 bytes off, just like last time. So every time you have a call instruction, it's going to use up 8 bytes on the stack. Okay, so let's check out what those 8 bytes are storing. Okay, the 8 bytes on the stack right now. Question?
So it's 8 bytes per subroutine, or
it's 8 bytes per call.
per call?
Yep, per call. Every time you use call, it's using up 8 bytes, but that's only because I'm using a 64-bit architecture. In your case, using the emulator, it is 32-bit, so it's only going to use up 4 bytes.
4 bytes, and that's going to be using the pointer ESP.
Let me just do everything in the emulator, so this way it maps to what you will actually see. Okay, so let me just kind of get out of this one. I'll copy everything into the emulator. So the first thing to do is to start the emulator. Because otherwise, what you see, with my example doesn't map directly to what you are going to see in your case. So I don't really like that. So I'm going to copy everything onto the other side. So we'll do a tar CZBF call a subfolder user at dash p. Okay, connection to host 2200. Lowercase p there. The default password is live, I think. Nope. User. There we go. Okay, so now when I SSH into the virtual machine, I should see all those files. There we go. So I got everything here, but I do have to reassemble and relink because otherwise it's the 64-bit version. So we'll do another assemble. And another link. Now we can do another debug session, but this time this is exactly what you should see when you debug this in the 32-bit emulator. Okay, put a breakpoint at _start, run the program, IRESP in this case because it's a 32-bit register. Single step, IRESP again, and you can see this time it's only off by 4 bytes because C is 12 and 0 can be interpreted as 0. It can also be interpreted as 16. So 16 minus 12 is 4. So the question now is, what exactly did we store on the stack that took up 4 bytes? Let's take a look. The X command will do this, x/wx, which is 32-bit wide in hexadecimal, and exactly where the stack pointer points to, because remember, the stack pointer points to the very last thing that we just pushed. So this will show us what is there. Okay, 08048059 doesn't seem to be interesting or of any importance. Remember those 2 extra labels that I defined? One is called after call G, right? Let's find out what that label is defined to. So I'm going to kind of do a print. I think in this case I need an ampersand because the debugger gets confused because of the lack of types. So we'll take a look at after call G. Do we see anything that's related? So what just happened? Can someone tell me what happened when I execute the instruction call G? The stack, okay, we use the stack space, okay, we use 4 bytes on the stack. But what did we store on the stack?
The label.
No. Okay, so we can see 2 numbers being the same here, okay? The stack pointer is pointing to 32 bits that turns out to be the address of whatever instruction is after the call G instruction. It's the address of whatever instruction is following the call instruction. It uses 4 bytes for that. It's a 32-bit address, and that's why it's using 4 bytes on the stack. So a call instruction is really doing 2 things, okay? The first thing it does is to save the address of the instruction immediately following the call on the stack. That's the first thing that it does. The second thing it does is a jump to the label that you're calling. Is that okay? Why do we have to save that address on the stack? No, it doesn't need to know that. Why do we need to save the return address?
Oh, when you go back.
Well, the name of that thing, return address, is kind of suggesting what it's useful for. It is used for returning. Very good. Because at the end of a subroutine, you don't have a go-to. How does it know where to continue execution at the end of a subroutine? It checks the stack. It will say, whatever the stack point is pointing at right now, is going to store the address of where I need to go. That is what the return instruction is going to do. So we'll get to that point, okay? So right now we are now pausing or stopping at the instruction call F, which is a part of the subroutine G. So let's single step this one. Single step, we are now in the subroutine F, which starts with the no-op instruction. The no-op instruction literally doesn't do anything, okay? Which is not what we are interested in. But what we are interested in is the stack pointer. So the stack pointer is now decreased by another 4 bytes because it used to end with 9C, now it's ending with 9.8. So we just used up another 4 bytes on the stack. So that means we saved something that is 32-bit wide on the stack. Let's find out what we just stored. x/wx $ESP. It stored another number that's kind of similar to the first number. What do you think this number is corresponding to? This is something that we just stored on the stack when we call F.
Jump from?
No, this is the address of, this is the address of the instruction immediately after the call F instruction. Hey, don't we have a label to remember that particular location? Let's check that. So we say print the address of after call F, and they're exactly the same. Okay? So now we'll single step through the no-op instruction, which doesn't do a single thing, and now we're at the return instruction. So the return instruction is supposed to continue execution at the instruction right after the call F instruction. But how does it know that? That is on the stack. That's why it knows. So when we single step the return instruction, it knows to go back to the previous location. So when we look at the instruction pointer right now, okay, so let's do that. IREIP, which is the program counter, which is also the location of this return instruction. Haven't we seen this before? I mean, it even spells out the label that is exactly the same value. Okay, which label are we talking about? After call F. Okay, but this is where we are executing at this point. In other words, the return instruction is basically looking at whatever the stack pointer is pointing to, grab those 32 bits on the stack, and say, hey, these 32 bits is telling me where to continue execution. And it will just continue execution at that location. Do you think those 32 bits is of any use anymore at this point? The return address to get to after call F, do you think those 32 bits is useful at this point? No? So it should no longer be on the stack. It should be popped, right? But pop doesn't really destroy anything on the stack. What does it do instead? No. It changes one register to basically say, oh, okay, the useful part of the stack is now up here.
The pointer.
It changes the stack pointer by 4. Okay? So the return instruction should do exactly the same thing. It's kind of like a pop, right? It has an implicit pop in it. So when we look at the stack pointer, ESP, what is it now? It's at 9C. What was it before the return instruction? Let's check. Before the return instruction, it was at, oh, it was on the screen earlier. It was at 9C, 9.8 at this point, and now it's over at 9C. It has increased by 4. When the stack pointer increases, it means we have deallocated something on the stack. And that's the return address. Is that okay? But we are now at another return instruction on line 14. So when we execute this return instruction, it will continue execution at whatever address is stored on the stack right now at this point. So let's check that right now. We will take a look at whatever the stack pointer is pointing to, because that is going to be the location where we are going back to. So the location that we're supposed to continue execution ends with 5.9. And we'll go ahead and single step. Single step. This doesn't tell us, what the location, so we'll take a look at EIP. And do you see anything related here? It used the address stored on the stack as a location to go back to. So we are now continuing execution at location 08048059, which is according to whatever is on the stack.
So like you just where it has the stack, that's where it goes to next.
Correct. The stack is being used to store the return address. The return address is literally the address to continue execution when you execute the return instruction, when you're at the end of a subroutine.
Of the function. Of the function.
A function, subroutine, they are basically the same thing. Right.
So like when it goes to that function, it goes back to where it was called from and it just continues. Right?
Okay, let's take a look at the whole source code so we can see the whole thing a little bit better. Call return.s. There we go. So what is happening here is, let me turn on the line numbers. So what's happening is on line 4, when we execute the instruction call G, it is doing two things. The first thing it does is to save the address after call G on the stack. It's the same thing as a push $L after call G. Okay? And then the second thing it does is to continue execution in the subroutine that we are calling, which is G. Yep, go ahead.
So it's gonna say first the return address the call G.
Okay, so let's see if we can express this using other instructions. Okay, so call G is really doing these two things. The first thing it does is a push $L after call G.
The address.
The address, yes. This is the address of the move $L$1 instruction. Okay, so it's going to save that on the stack first because the return instruction is going to make use of this.
When it gets out of that.
When it gets to line 15.
Yeah. Okay.
Okay. But then the second thing it has to do is just an unconditional branch to the subroutine that we're calling. Because a call instruction has to continue execution in the subroutine that we're calling. So that means, the call G instruction can literally be replaced by these two instructions. They would have done exactly the same thing.
So it's gonna go home and then go back where it was.
That's how we remember where to go back to.
Yeah.
All right. So that also means the call F instruction is the same way. I can replace the call F instruction with push $L after call F, and then we continue execution at the subroutine F, which is done by jump F, just like that. Is that okay? Any questions about this? What about return then? What about return? Because return is supposed to pop the address from the stack and continue execution at that particular address. Okay? Which means it's the same thing as popping into EIP, because whatever we pop is being stored into EIP. So that means it is doing the same thing as pop L %EIP. But if you try to write the instruction pop L EIP, your assembler will complain because there's no such instruction. You cannot access EIP directly. It's just not possible. So what do you do instead? This is what we want to do, but we cannot do it because the assembly language does not have an instruction for this. So instead of doing this, we can pop L into a register, which will destroy the content of EAX. So if EAX is useful for something else, it's going to be overwritten. And then we can do a jump to whatever EAX is indicating. Most people would say, hey, it's the same thing as an indirect because it seems to make sense. Whatever EAX is indicating the address, but that doesn't work either. The syntax has to be this, which literally means copy the 32-bit in EAX into the program counter or the instruction pointer. Is that okay or not? Okay. So there you go. That's calling and returning. Okay, they are definitely stack-related operations. But if you remember from the previous class, we also said that push and pop are CISC instructions. Do you guys remember that? Complex instruction set computer instructions. So that means we should be able to boil this all the way down to something that is just move, add, subtract, and stuff like that. So let's go all the way to talk about the most basic instructions. So pop EAX is done by move L, whatever the stack pointer points to, into EAX, add L $4 to ESP to reclaim those 4 bytes on the stack. And then we do a jump asterisk $EAX. So these 3 instructions can replace the return instruction. And then for push L, it can be done by the usual move and add instruction. So we can say this is the same thing as subtracting 4 from the stack pointer. And then we are copying the label after call F to whatever the stack point is pointing to, and then the jump F instruction. So a call can now be done by 3 instructions and an additional label, and the return instruction can also be done by 3 instructions. But we have just boiled everything down to all the really basic instructions that we have always been talking about, except for the jump instruction at the very end here, because this is something that we have not talked about. Because we have always used a label to indicate where to continue execution. This one is basically saying, oh, we'll continue execution at the address that EAX is pointing to. So that's the only difference. That's the only new thing that we have talked about. Are there any questions about the call instruction or the return instruction? No questions? Yep. Mm-hmm.
You want us to use, we're not going to use call and return, we're going to use
No, you guys can use call and return. I just want to show you, in the absence of call, return, push, pop, we can still accomplish exactly the same thing using much more basic instructions. Because remember from last time, the previous discussion, I want to teach this class in a RISC way, R-I-S-C, RISC way, so that you guys understand how to do this is using the most basic instructions. Even though in the CISC architecture, we have really handy instructions to do everything with only one single instruction. Okay. Yep.
So if there was something useful in EAX, how do you...
If you do have anything useful in EAX, you have to choose another register.
Or save
But
it
it
to
will
memory.
chew up one register, unfortunately. Yep, go ahead.
Or you could save it to memory and then use it in case they're all important. And then
But where do you save it? Because you are using the stack. So it's kind of tricky because that's why calling and returning is usually available even on RISC architectures. The ARM architecture, even though it is the most common and the most cost-effective RISC architecture, actually has call and return as instructions. Because it is so commonly used, it doesn't make sense to have to break it into 3 instructions every single time. So that's why even with a RISC architecture, and this is not exactly a RISC instruction, it is commonly implemented as one single instruction just because it is so cost effective. Okay, any other questions? Okay, so after this, we will start to get into parameters and also return values. Okay, how do we specify parameters when we call a subroutine? And when, at the end of a subroutine, how do we return values in the subroutine? So if you have time over the weekend, you're just going to read ahead of me a little bit. Yep.
On the homework, Can we use registers besides EAX and EDX?
Yes.
Okay.
So you can use EBX, ECX, as additional registers.
Okay. If we don't use any of the new jump, pop, push, etc., we get marked down for that.
Can you ask the question again?
Yeah,
If